SwayamPrabha. Digital India. Educated India.
Dear learners, welcome to this course Applied Thermodynamics Module 5 Refrigeration and Air Conditioning. So, as I discussed in the last class, there are 6 lectures and first 2 lectures will be on vapor compression refrigeration systems, and we are in lecture number 2, that is vapor compression refrigeration system part 2. So, in this lecture our main intention would be to discuss about actual vapor compression systems. In our previous class we have analyzed a ideal vapor compression systems consisting of condenser, evaporator, compressor and a throttling valve, and that was the ideal case of operations. Now we will look into the actual vapor compression systems, in which we will introduce irreversibilities into the components of the vapor compression system. Apart from that, we need to discuss something on pressure enthalpy diagram. This is similar to the idea of properties of your substance, and here we are using a refrigerant, and this refrigerant, if you consider it as a pure substance, we can draw its thermodynamic diagrams, and one such diagram which is used in the refrigeration systems more commonly is known as a pressure enthalpy diagrams. Apart from that, there are other diagram also, temperature entropy, and these are very commonly used in a refrigeration systems. This is similar to the fact that when you use Otto cycle, PV diagram and TS diagrams are very common. Even for diesel cycle, for Brayton cycle it is PV and TS diagrams are very common, but here the common diagrams are pressure enthalpy and temperature entropy diagrams. Apart from this, we will also discuss about vapor compression heat pump systems. So, all these things we talk about vapor compression refrigeration systems. We will next segment would be vapor compression heat pump systems, in which it is similar to a refrigeration system, but desired effect is little bit different. And towards the end of the lecture, we will discuss about gas refrigeration systems, in which your working fluid is taken as air and it operates on a reverse Brayton cycle. This is the entire summary for these lectures. So, let me start with the ideal vapor compression systems, which we stopped in the last class. So, a complete vapor compression refrigeration cycle consists of series of internally reversible processes except throttling. So, these components are evaporator, in which heat is added from the space to be cooled, and in which refrigerant takes the through this process refrigerant changes its phase from liquid state to saturated or superheated vapor states. Then it expands in the compressors where work is being fed by external agency, and then after compression the pressure of refrigerant rises to condenser pressure, and then when the refrigerant enters to the condenser, it releases heat to the ambient. As a result, it again changes its phase from vapor to liquid. Now, this already when it is changes its phase, but still it is at condenser pressure. We have to reduce this pressure of this refrigerant. back to the evaporator pressure. So, we require an expansion valve. So, or simply we call this as a throttling valve. Then it comes back from state 3 to state 4 and again the cycle continues. The thermodynamic diagrams in TS plot refers 1 to S compression process, 2S to 3 condenser process, 3 to 4 throttling process, 4 to 1 is evaporator process. And for this we can calculate cooling load from in the evaporator, that is Q dot in by M dot, that is H 1 minus H 4, compressor load W dot C by M dot, that is H 2 S minus H 1, Q dot out condenser load Q dot out by M dot is H 2 minus H 3, and in a throttling process it is H 3 minus H 4. And finally, we can calculate the COP, that is beta, which is nothing but desired effect. Here it is Q dot in by M divided by W dot C by M. So, it is H 1 minus H 4 divided by H 2 S minus H 1. Now, we will relax this ideality and try to introduce some kind of irreversibility into the systems. So, that is what we say, it is a actual vapor compression systems. In a actual compression system, I mentioned the first thing it departs is that your condenser pressure as well as temperature is higher than that of the warm region temperatures. So, that means condenser temperature is higher than the warm region temperature and the evaporator temperature is lower than the cold region temperatures. Then only the vapor compression system can works efficiently. So, in ideal system, process 1 to S is isentropic, process 2 3 is a constant pressure process, throttling process 3 to 4, and finally 4 to 1 is the evaporator process. But if you see this particular diagram here, when you refer the TS diagram for an actual process, we can say there is a dotted line here. It seems that we have introduced the efficiency for the compressors, and we call this as an isentropic efficiency of the compressor. So, the second other important aspects of this diagram is that if you can see here in a ideal diagram, the refrigerant has to leave at state 3 from the condenser, and the state 3 is the saturated liquid state, but it may so happen that we can extend it further. The refrigerant can come back to subcooled regions, where in actual diagram it is represented in the state 3 here. So, in this way that refrigerant can be a subcooled situations. So, this is basically done just to enhance the refrigerating effect, because the point 4 will be accordingly located on this diagram slight bit. So, that evaporator load also increases. Then another important aspect is that from when the refrigerant leaves from the evaporator, in a ideal system it is exactly at saturated vapor state 1, but in a actual situation the point 1 may lie in a close to superheated regions. So, these are the some features that actual vapor compression system differs from an ideal system, and based on that one can first thing one can introduce here is the isentropic efficiency of the compressor, that is isentropic work which is fed compression system, that is W c dot by M, that is isentropic work, to the ideal work will be more. So, that is W c by dot by M. So, in a sense that the isentropic efficiency of the compressor can be represented in the form of enthalpies at the state points, that is H 2 S minus H 1 divided by H 2 minus H 1, and as you see in this diagram, obviously the denominator number is higher because point 2 lies above 2 S. So, this is how we say the isentropic efficiency of the compressor is introduced in an actual systems. And moreover, if you look at here, and in this process of introducing irreversibilities, the COP decreases because the average temperature of refrigerant in the evaporator decreases and average temperature of refrigerant in the condenser increases, and both these effects ultimately leads to the decrease in the COP. And this also I have explained the two other important aspects, that is superheated vapor condition at the evaporator exit and subcooling condition at the condenser exit states. Apart from this, there are additional departures from the ideality of stream are frictional effects resulting from pressure drop of refrigerant through the evaporators, condenser and the piping systems. Of course, in our calculation we normally do not take into account for solving the problems unless and until it is very elaborately specified. Okay. Now, we will move to the thermodynamic property evaluations. So, as I mentioned in our earlier analysis, that either whether it is a ideal vapor compression system or actual vapor compression systems, and we, in order to know the performance of each component like condenser, evaporator, throttling valve, compressor, for all these components it requires the evaluation of properties values at state points, and in particular the properties values that are important to us are enthalpy and entropy, and of course condenser pressure or condenser temperature, evaporator pressure and evaporator temperatures. Considering these aspects, there are two important property diagrams that are explained here. One is temperature entropy diagram, which is also very common in all our thermodynamic study. Apart from that, another diagram that becomes very important for a refrigeration system, that is pressure enthalpy diagrams. So, we will try to say that what is the significance or why these diagrams are more important. First thing we know that since we are talking about temperatures of cold region and hot region or warm region, then we must have one axis which talks about temperature. So, that is what we can say, it is a temperature in one of the axis. Other part is that when you side by side when you talk about temperatures, we also have talked about the pressure, and because it's the property of refrigerant when you deal with, we have two states, saturated liquids, liquid vapor mixture, saturated vapor, then superheated vapor, and to cater all these state points we require information for both pressure and temperatures. That is what in one of the axis the pressure and temperature comes into picture. And other aspect is that now when you deal with the thermodynamic processes, the other important property that becomes vital is entropy, because a compression process, first thing we say it is isentropic process, and also in a sense that when you talk about throttling, so enthalpy becomes a significant properties where temperature, where enthalpy does not change. So, if you take all those parameters in their respective axis, that means then it becomes easy for us to locate the state points. So, that is the reason these two, temperature entropy and pressure enthalpy, are taken for discussions. So, if you look at the temperature entropy diagrams, 1 to S is isentropic compression, 2S to 3 is constant pressure heat rejection in a condenser, 3 to 4 it is a constant enthalpy process, 4 to 1 is evaporator process or constant temperature heat rejections. Now, if you look at within the dome, we can say irrespective of whether you take TH diagram or PH diagram, this line is a straight line within the dome. Okay. So, the line is a straight line, and and also if you look at temperature and entropy diagrams, constant pressure line is also in this falls in the same straight line, and even if you look at within the dome of pressure enthalpy diagram also, here evaporator temperature and pressure remains the same dome, within the dome they are straight lines. So, it is easy to locate those properties. So, that means whether you talk about pressure or temperature based on the property table, either properties table for saturated state, from pressure table or temperature table one can look at the properties. That is one aspect. Other aspect is that if you look at temperature entropy diagrams, the process 3-4 is a constant enthalpy process, but interestingly it is a inclined straight line. Okay. And that means in a temperature entropy diagram this enthalpy lines is a inclined straight line. So, this is also, and of course, it is a irreversible process, but it is a inclined straight line, and in a 1-2s is isentropic process. So, it is a vertical straight line. Now, if you come back to pressure enthalpy diagram, the process 1 to 2s, which was supposed to be a vertical straight line, now it becomes an inclined straight line, as you can see in a pH diagram 1 to 2s. And of course, 2s to 3 is a constant pressure process. From 2s to 3 you can draw a straight line from 2s to 3, and 3 to 4 again it is a constant enthalpy process. So, it is a, and from 4 to 1 it is a evaporation process, which is again a constant pressure process. So, if you look at this diagram, most of the lines are almost straight line, and because of this reason, so it is these two diagrams are normally preferred. Okay. And here also there is another way that we can evaluate the thermodynamic property table from for the refrigerants. So, normally when you deal with the steam tables, the water was taken as the steam tables, water was taken as the working fluid, and in fact, it is used in the power plants, mainly steam power plants, to look at the thermodynamic properties. So, in that water steam property evaluation using steam tables, we have properties based on temperature table, properties based on pressure table, that was done for the water, but here the working fluid is refrigerant. So, let us talk only one particular refrigerant, and this particular refrigerant is a very common nowadays, that is refrigerant 134A, and for that refrigerant we can have the similar property tables which are available in the books. So, reference book would be this Moran and Shapiro, Principle of Engineering Thermodynamics, John Whaley and Sons. So, you can refer this table A10, A11 and A12, from which these extracts are taken, and these tables are exhaustive tables that gives properties in 3 sequences. One is liquid vapor table, and based on the temperature data. That means, if you know the temperatures, that means in one axis corresponding saturation pressure is field known, and accordingly all thermodynamic properties like specific volume, internal energy, enthalpy and entropies can be calculated. The other variants for this, if you know the pressure range, like if you know condenser pressure or evaporator pressure, then you can use this pressure table, and then from the pressure table corresponding saturation temperature is known. So, now from the pressure table, say exactly in a similar manner we can calculate specific volume, internal energy, enthalpy and entropy. So, this is how the properties are evaluated within the dome. Within the dome, I mean the saturated liquid, saturated vapor, or or we can say some cases we say it is a dryness fraction or something else. So, in this way we can do this, and apart from that, when you go to the superheated region, now in our thermodynamic states, our superheated region comes in the state 2s, when the refrigerant comes out of the compression systems. So, there only it is it is in the superheated regions. For those regions we can also use the superheated vapor, and for that we require 2 parameters or 2 data. One is the pressure data, other is the one of them either specific volume, internal energy or enthalpy or entropy. But here since our entropy remains constant during the compression process, so the apart from pressure or temperature we also have we require entropy. So, from pressure entropy we can evaluate the states of thermodynamic states of the refrigerant in the point 2s. So, this is how the property is going to be studied for the either in the form of TH diagram, pH diagrams and in the way of determining the properties using the tables. And similarly, this table is done for refrigerant 134A, but similar property tables can also be possible for other refrigerants. Other refrigerant could be R11, R22, all such refrigerant, or it could be ammonia, it could be carbon dioxides. For all of them, the property tables are available in the book. But from our course, we will basically stick to one particular refrigerant, and for that refrigerant we are going to use the property values using that table. Now, we will move to the heat pump systems. So, the heat pump systems are normally operate in a opposite manner as a that of refrigerant system. By opposite manner, I mean that your desired effect comes from the condenser side, not evaporator side. So, that means the heat load that comes out of the condenser is getting used by some kind of apartments or rooms which is needs to be heated. So, that is the main intention of this. So, if you look at this particular diagram, almost it operates in the same manner as is done, but the desired effect is different. So, the objective of the heat pump is to create desired effect above the surrounding temperature or elevated temperature required for industrial processes. And it has many common features with the refrigerant systems, and more importantly, the heat pump systems can be operated either in a vapor compression mode or also it can be used at a vapor absorption mode, and in its later part we will see that how it can be used at a absorption mode. And in your most application you will see that when you deal with the heat pump systems, normally they are integrated with the vapor absorption systems, because we can tap the low grade energy for its usage in these heat pump applications. But whereas mostly when you talk about refrigeration and air conditioning plants, they are based on the vapor compression mode, and normally vapor compression heat pumps are suited for space heating applications, whereas absorption heat pumps use low grade energy mainly used for industrial applications. The most possible sources of heat transfer to the refrigerant passing through the evaporator are outside air, ground, lake, river and well. Normally in our things that from this evaporator we normally talk about atmospheric air or outside air, and there are other ways that we can take out from the evaporator side. We can also use ground, lake, river, well, all these things are possible sources of heat transfer. The other type of heat pump systems which are mainly common is shown here, we call this as a reversing heat pump mode. And in a heat pump mode, I mean when you deal with a industrial mode of heat pump, we also have to see that it can cater the need of heating as well as the cooling. So, whenever it is required we can switch it to a heating mode, and when it is required you can switch it to a cooling mode. So, for that things the components are designed in a such a way, so there are some kind of valves which operate in a reverse manner. So, we call as a reversing valve. So, by reversing valve I mean we can control or regulate the direction of flow of refrigerant within the components, and so in a heating mode the refrigerant will follow in one sequence and their sequence will be reversed when you go for a cooling mode. So, based on this it can cater the need of both heating as well as cooling applications. So, this is how this complete heat pump systems is defined. Either it can be a space heating as it is in the first figure, or it can be a heating as well as cooling mode by using a reversing heat pump. But what we are basically interested in a heat pump systems, and our main intention is that the desired effect that comes out is mainly on space heating. And this is how for the heat pump basic theory that pops up, and it comes from the basic Carnot heat pump cycles, where we can draw again this TS diagram, and from this TS diagram and with the components involving evaporator, compressor, turbine and the heat pump operating between warm region TH and TC, one can calculate the COP, and here the COP is represented, just to make a notation change, that is you can say it is a gamma. So, when you say COP for heat pump, we normally represent in the form of gamma, or if I read gamma, it means that it is COP, but it is meant for heat pump. And when I say heat pump, your desired effect changes, that is here it becomes Q out, that means heat rejected to the warm regions. And in the denominator, your compression work remains same. Now, by locating the states point 1, 2, 3, 4, one can calculate the area under the diagrams, and from this area diagrams we can calculate the maximum COP, or we can say Carnot COP for a heat pump as TH divided by TH minus TC. And we cannot operate a Carnot heat pump, because actual heat pumps have COP lower than the maximum COP. So, we have to switch over to a realistic versions. So, we come back again to a vapor compression mode heat pump systems, and this is done in a similar fashion as we did it for vapor compression refrigeration systems. And there we say the your COP becomes gamma, and this gamma is of course less than gamma max, that is Carnot COP. And based on that, the vapor compression heat pumps are evolved. So, if you this is the circuit diagram for a vapor compression heat pump systems involving condenser, expansion valve, compressor and evaporator. And moreover, the TS diagram also represented as 1 to 2S compression process, 2S to 3 condenser process, 3 to 4 throttling process and 4 to 1 is the evaporator process. But the role of evaporator is not felt here, rather this particular part, that heat that goes out of from the condenser becomes very vital as a desired effects. So, if you see here, the expressions that are of interest to us is W dot C by M, that is compression work H2S minus H1, and Q dot out by M dot is H2S minus H3, and this is the very vital part, because that heat goes to the used for space heating. Of course, we can that heat, when you are getting utilized, we have to also calculate evaporator load as well, which is Q dot in by M dot, that is H1 minus H4. Again throttling process H3 is equal to H4, and finally COP for heat pump, that is equal to gamma, that is equal to H2S minus H3 divided by H2S minus H1. So, the heat pump and here the net work input required to accomplish this effect comes from the electrical heating load. And here we can see that the COP can never be less than unity for a heat pump. We also mentioned that COP of heat pump is COP of refrigerator plus 1. The next segment in our discussion is a gas refrigeration systems. So, in a gas refrigeration systems, here the main important aspects of a vapor compression systems or vapor absorption system with a gas refrigeration system is that here you are using gas as a working fluid in the refrigerations, and in particular if gas is a air, then we can say is the air is used as a cooling medium or in the working fluid in this thermal circuit. And when you use the air, and here main assumption is that air does not change its the phase, but it can be temperature of air can be lowered by using a gas refrigeration cycles, and through this process we can achieve the refrigerating effects. And when you are using air, we can have to recall a Brayton cycle in a gas turbine engines. When you are using it for power production systems using a Brayton cycle, there you used to have a turbines, and our main intention is that that point of time was power output from the turbine. But here we will operate that Brayton cycle in a reverse mode, and we call this as a reverse Brayton cycle, and it is considered as the basic gas refrigeration cycle with air as a working fluid. So, here the term that we are going to use, of course, turbine compressor integrated systems. The turbines, some power when the air expands in the turbine is going to be used to drive this compressor, and side by side there are two exchangers involved, and here the here you not use the word evaporator or condenser because there is no change in the phase. That is the reason we use the word heat exchanger. So, if you look at the, and of course, this particular cycle, so you can say it is a reversed heat engine operating between the cold region Tc and warm region Th, and where it takes some kind of work input into the systems. As a result, it is possible to extract heat from the cold region and send it back to warm regions. And when you deal with the Brayton cycle, the common diagram that is dealt was the temperature entropy diagram. And if you look at these thermodynamic processes of each components involved in a gas refrigeration systems, we can see the in a compression the process is ideally it is an isentropic process 1 to 2s. If isentropic process is relaxed a bit, so you can introduce some efficiency or introduce a reversibility, the process goes from 1 to 2. So, we call this as a isentropic, or you can say isentropic efficiency for the compressors, and 2 to 3 process is a constant pressure process, and it is a heat rejection in the heat exchanger, and this heat exchanger is integrated with the warm region. So, where heat is released from air to this warm region. Now, the air that comes after this heat exchanger, it expands in a turbine in which power that comes out. Now, when it comes out the power, this power is typically used to drive the compressors. Now, when it reaches 3 and 3 to 4 is a again the expansion in the turbine process, and remember this turbine process we use the word turbine in a gas refrigeration systems, but in a vapor compression system you use the word expansion valve. That is the basic difference, we must take a note of it. So, the process 3 to 4 ideally it has to be an isentropic process. So, 3 to 4s is an isentropic process, but if you introduce efficiency in the turbine systems, we can say it is an isentropic efficiency for the turbine. So, actual process goes from 3 to 4. Now, again from 4 to 1 it is the second heat exchanger that is getting utilized by taking heat from the cold regions, and from process goes from the 4 to 1. So, this is how a gas cycle system operates. So, I have elaborated it. Air enters the compressor at state 1, temperature is slightly less than the cold region. Air undergoes isentropic compression till process 2s, till the state 2s is reached, and from 2 to 3 it is an heat exchanger, it goes into an heat exchanger where it approaches the warm region temperatures. Air expands isentropically to state 4 in which it is well below the temperature of cold region, and refrigeration effect is achieved through the heat transfer from the gas as it passes from 4 to 1 by completing the cycle in a second heat exchanger. So, if you look at the actual cycle is 1, 2, 3, 4, and if you say ideal cycle it is 1, 2s, 3, 4s. And some important features are that at steady state specific work output from the compressor and turbine can be calculated. One can also calculate the magnitude of work developed by the turbine is quite significant, and it is as compared to the compressor input. So, that is what the turbine work input is getting utilized to drive the compressors. And the refrigerating effect is the heat transfer from the cold region to the air circulating through the low pressure at heat exchanger. One important thing here I just want to point out that when you talk about air cycle refrigerations, and we also of course, it gives a desired refrigeration or cooling effect, it is very difficult to take to cater the need the subcooled region temperature below 0 degree centigrade using a gas cycle refrigeration. So, it is normally required when the temperature in the cold region is not significantly low. Now, using the concept of Breton refrigeration cycles, one can calculate the compression work per unit mass of air in the form of enthalpy H 2 minus H 1, then turbine work is H 3 minus H 4, heat input that is H 1 minus H 4, and your COP that is beta, and here you are using again beta because you are talking about refrigeration cycle or you are talking about refrigerating effect. So, you can again calculate from the coordinates of enthalpies H 1 minus H 4 divided by H 2 minus H 1 minus H 3 minus H 4. And apart from that, by talking while talking about gas refrigeration, we also talk about the efficiency of the components, and here mainly isentropic efficiency of turbine and the compressors. And based on the state point calculations, we can use the values based on their isentropic values as well as the actual values. So, for instance, if you take about turbine efficiency, it is the actual turbine work to the isentropic work, and from this diagram we can actually calculate isentropic efficiency of turbine is H 3 minus H 4 divided by H 3 minus H 4 s, and for compressors the isentropic efficiency of the compressor is H 2 s minus H 1 divided by H 2 minus H 1. And moreover, another point I need to emphasize, since it is a air, we can use the simple equations like enthalpies can be written as Cp times T for air. That means, instead of enthalpy, it is also possible to evaluate the properties by changing by knowing the temperatures. So, it just that means, if you take H enthalpy, you can take it as a Cp times T. So, of course, we all know that for air cycle refrigerations, the first step that you need to know the cardinal temperatures of each points in the cycle has to be noted first. So, once you note the temperature, then when you multiply Cp value of air, then you get the enthalpies. So, likewise, this gas refrigeration cycle can be analyzed. Now, we will try to solve some numerical problems based on the topics that we covered today. The first problem is based on a vapor compression cycle that operates a cold region, that is 0 degree centigrade, and warm region 26 degree centigrade, and it uses refrigerant 134A as a working fluid. That means, temperature of cold region and warm region is given. But in this cycle, how it operates? Saturated vapor enters the compressor at 0 degree centigrade. That means, your cold region temperature as well as the refrigerant, they are at same temperature 0 degree centigrade, and saturated liquid leaves the condenser at 26 degree centigrade. Again, at the condenser side also they are same, and also other parameter is mass flow of refrigerant is 0.09 kg per seconds, and we have to calculate compressor power, refrigeration capacity, COP, and of course, Carnot COP with same operating temperatures. Now, first thing we need to I need to emphasize that here we need the property data for refrigerant 134A. So, that is what I have taken the extracts of the data from the book, and these extract of the data are written here, and these extracts are nothing but the properties values that are required for us to solve the problems. Okay, so for example, here you require the temperature 0 degree, 26 degree centigrades, all this for, and of course, in some situations you also require the superheated data when you deal with the compressor. So, that is the reason we have to use the data table from the book. Now, to solve the problem, the first thing that we need to do is that we have to draw your temperature entropy diagram. This temperature entropy diagram, for this we can first prepare a dome. So, in the dome we can say there are two straight lines which are horizontal, and these are nothing but your constant pressure lines, and but outside the dome this constant pressure lines becomes in this fashion. So, we can locate the state points as one, 2s, 3, 4. 1 to s is compressor, 2s to 3 is condenser, 3 to 4 is throttling, 4 to 1 is evaporator. Now, the data that is given, if you draw this line, it is 0 degree centigrade for evaporator and it is 26 degree centigrade for condenser. And if you draw actually its circuit, so basically it is a refrigerator, and the warm region temperature is TH 26 degree centigrade, and that 26 degree centigrade means 299 Kelvin, and in the cold region we have 0 degree centigrade, that is 273 Kelvin, and for this we also require W dot in. So, we take Q dot in and you have Q dot out, and here Q dot out is nothing but your condenser load, Q dot in is nothing but your evaporator load. So, these things we are given with us. Now, to solve the problems you have to use this property table. So, first thing how to use the property table. So, at 0 degree centigrade, and for this refrigerant 134A, if you look at here, so we can evaluate. So, the point 1 is it saturated vapor. So, saturated vapor we require enthalpy values Hg, Sg. So, we can write as H1 as 247.23 kilojoule per kg Kelvin, S1 as 0.919 kilojoule per kg Kelvin, or it is a kilojoule per kg, enthalpy is kg. Now, process, once we know this, we have to go to, that is we know state 1. Now, state 2 we require, it is a isentropic process, 1 to 2s is isentropic and 2s is in the superheated region. So, for this region what we that means S2s is same as S1, and that is 0.919 kilojoule per kg Kelvin, and S2s is there, and this 2s stands in the condenser temperatures. So, that means at 26 degree centigrade one can find out what is the saturated pressure. So, you refer here, so 26 degree centigrade, we can say saturated pressure is 6.853 6.83 bar. So, basically to calculate state 2s, we have pressure 6.853 bar and entropy 0.919 kilojoule per kg Kelvin. So, for that we have taken the superheated value close to a value of 7 bar and entropy value 0.919. So, this gives the enthalpy value is this. That means, we can know H2S is equal to 265.37 kilojoule per kg. So, H2S is known, and for state point 3, it is 26 degree centigrade or and enthalpy values at this point will be saturated liquid state. So, 26 degree and saturated liquid state 85.75. So, H3 is 85.75 kilojoule per kg Kelvin, and this is also equal to H4 because H3 is equal to H4 throttling process. So, through this process we all know enthalpy at every point, and we also know mass flow rate is equal to 0.09 kg per second. Now, it is easy to calculate the properties. So, say W dot C is equal to m dot H2S minus H1. So, m dot is 0.09, H2S 265.37 minus 247.23. So, this number is 1.63 kilowatt. Then refrigeration capacity, that is Q dot in, that is m dot H1 minus H4, that is equal to 0.09 into 247.23 minus H4 is 85.75. So, this is 14.53 kilowatt. Now, this when you divide it by 3.52, so this is will be 4.13 ton, because it is required at ton. Third is COP, that is beta Q dot in by W dot C. This number will be 14.53 by 1.63, it is 8.9. Last is Carnot COP. So, beta max is nothing but Tc divided by Th minus Tc. So, that is 273 divided by 299 minus 273. So, this number is 10.5. So, your maximum COP is 10.5, but actual compression system that as COP is 8.9. So, this is how it is solved. Then the next question with same data in question 1, it is the question is little bit shifted to the fact that instead of refrigerant and refrigerant is temperature and your condenser or evaporator region temperature in the same to be same, we have changed the problem to fact that the saturated vapor enters the compressor minus 10 degree centigrade, whereas your cold region temperature is 0 degree centigrade, but the refrigerant is now below this. So, minus 10 degree centigrade, and the saturated liquid leaves at the condenser pressure of 9 bar. So, this is this saturation pressure at that point is higher than the hot region temperatures. So, for this modified cycle we have to evaluate the same thing. So, to solve this problem, we have to relook into our TS diagram in a sense that, so we can redraw this dome again. First thing we have to put a limit that what are the cold region temperatures. So, we have 0 degree centigrade and 273 Kelvin and 299 Kelvin. So, this is cold region and hot region temperature, but your cycle operates little bit different way. A condenser temperature is higher than the hot region temperatures, evaporator temperature is lower than the cold region temperatures. So, that way we can draw this line it is now 1, 2s, 3, 4. Okay. So, that this point we say it is a minus 10 degree centigrades and this is 9 bar, this constant pressure line is 9 bar. So, we have to calculate the values at these points only. So, in that sense, so we have to calculate the value at minus 10 degree centigrade. What value is required? We require, so minus 110 degree centigrade from the data, we have data from minus 12 and minus 8. So, we can interpolate these values, that means interpolate these values to find the data for minus 10 degree centigrade. Now, what data we require? We require H1. So, for H1 we take Hg because it is the superheated vapor. So, just take minus data for minus 12 and minus 8, add that, divide by 2. So, this number would be 241.35 kilojoule per kg. S1 also 0.9267 plus 9239 divided by 2, that is equal to 0.9253 kilojoule per kg Kelvin. Done. Now, S2S is equal to S1, that is 0.9253 kilojoule per kg Kelvin, and we also have 9 bar. So, P is equal to 9 bar. So, these two data gives the superheated regions. So, for 9 bar 0.92 value of entropy, we can say this will give H2S as 271.25 kilojoule per kg. So, this number, right, we know H2S. Then again at 9 bar saturated liquid table, saturated liquid table 9 bar. So, we can find out value as H3 value as 99.56 kilojoule per kg. So, that is also equal to H4. So, you know all the values H1, H2, H3, H4. So, we can find out first W dot C is equal to M dot H2S minus H1. So, this number would be 2.7 kilowatt because all the data are given here. Then refrigeration capacity Q dot in will be M dot H1 minus H4. So, this value would be 12.76 kilowatt. Third one beta, that is COP Q dot in by W dot C. So, this number would be 4.72. So, we can see that due to this irreversibility from the and when you compare with question 1, the compressor load increases, Q dot in drops, COP drops. This is due to irreversibility. Now, what is this irreversibility here? Because the cold region temperature is higher than the evaporator temperature, and the hot region temperature is higher than the hot region temperature is lower than the condenser temperatures. So, that is the irreversibility for which there is a drop in COP. Now, next problem is for a gas refrigeration cycle that operates in a ideal Brayton cycle. So, here we have to all first draw the temperature entropy diagram for a reversed Brayton cycle. So, we can draw in this diagram, we can draw the processes as 1, 2, 3, 4, and we can locate the points. Point 1 maybe somewhere here, T C T H. So, there are two pressures P1 and P3. This pressure ratio is 2.5. What are the data other given? P1 is 1 bar, T1 is minus 5 degree centigrade, that is 268 Kelvin. P3 is equal to 2.5 bar and T3 is equal to 25 degree centigrade. So, that is 298 Kelvin. For air we can take gamma as 1.4, Cp as 1.005 kilojoule per kg Kelvin. So, this data you require for air. Then we have to start the analysis. To start the analysis we have to recall isentropic relation. Now, for compressor and turbine you have to do, so you can say T2s by T1 is equal to P2 by P1 to the power gamma minus 1 by gamma. So, P2 by P1 is nothing but P3 by P1, that is 2.5, and we also know T1. So, this relation or putting the value we can calculate T2s as 2.5 to the power 0.4 by 1.4 into 268. So, this number would be 348 Kelvin. Similarly, from the turbine side we can write T4 by T3 is equal to P4 by P3 to the power gamma minus 1 by gamma. So, this will give you T4 as, because T3 is given. So, T4 you can calculate as 229.5 Kelvin, and we know rho of air, density of air we can write as 1.2 kg per meter cube. So, once you know air we can say mass flow rate, m dot would be rho air into volume flow rate, that is 1.5. So, 1.2 into 1.5. So, this will be 1.8 kg per second. Then we can now calculate one by one. W dot net, that is W c minus W t. So, we can write m dot C p T 2 s minus T 1 minus m dot C p T 3 minus T 4. So, by putting these numbers we can say W dot net becomes 20.8 kilowatt. Second part, refrigeration capacity, Q dot in is equal to m dot C p into T 1 minus T 4. So, by putting these numbers we will find 69.6 kilowatt. Third part, COP, that is Q dot in by W in. So, this number would be 69.6 divided by 20.8 is 3.35. Okay. Now, we will move to the last problem. This is in connection with the data from question 3, but here we have introduced the term isentropic efficiency. So, when you are introducing isentropic efficiency, then we have to recall our data based on the expression of isentropic efficiency. So, for this we can write this introduced isentropic efficiency per compressor, isentropic efficiency per turbine. To do this, first we have to recall the TS diagram. So, there we can say processes are 1, 2s, 3, 4, that is isentropic. Processes 1, 2, 3, 4, this is real process. So, isentropic efficiency per compressor we can write T2s minus T1 divided by T2 minus T1. Isentropic efficiency per turbine is T3 minus T4 divided by T3 minus T4s. So, these data are given to us, that is 0.8. Other fixed data are from the question 3. We have T3 is 298 Kelvin, T1 is 268 Kelvin, then T2s is equal to 348 Kelvin and T4s is equal to 229.5 Kelvin. Now, we also can calculate T4. T4 by using these equations we know T3, T4s. So, the T4 can be calculated as 243.2 Kelvin. Okay. Now, we have to calculate power input, refrigeration capacity and COP. So, the first question we can say W dot C compressor, that is isentropic compressor, that is m dot Cp T2s minus T1, that is equal to T2s is 348, T1 is 268 mass flow rate into Cp. So, this number would be 1.8 into 1.005 into 348 minus 368 268. So, this number would be 144.72 kilowatt. So, actual compression would be W dot C 144.72 divided by compressor efficiency. So, this number is 180.9 kilowatt. Then turbine work W dot T, that is isentropic, that is m dot Cp T3 minus T4s, that is 1.8 into 1.005, T3 is 298 minus T4s is 229.5. So, this number is 124 kilowatt. So, actual work W dot T would be 124 multiplied by eta T. So, this is 99.1 kilowatt. Then Q dot in is m dot Cp T1 minus T4. So, this will be 1.8 into 1.005, T1 is 268, T4 is 243.2. So, this number is 44.86 kilowatt. Okay. So, COP now becomes Q dot in by W in, that is 44.8 divided by W dot in. W dot in is W dot T minus W dot C minus W dot T, 180.9 minus 99.1. So, this value is 81.8 kilowatt. So, this is 44.8 is your Q in divided by 81.8. So, COP is now 0.55. So, how you can see that by introducing the efficiency of turbine, the COP has drastically reduced. So, this means irreversibility has a very detrimental effect in gas refrigeration systems. So, with this I conclude this lecture for today. Thank you for your attention.